Hey everyone, and welcome back to our Power Electronics series. In this explainer, we're doing a serious deep dive into a circuit that, honestly, is the very bedrock of the entire field, the half-wave rectifier. We're calling this an analytical masterclass for a reason, because if you can truly understand this one simple-looking circuit, you'll have the key to unlocking the most complex systems out there. So, let's get right into it.
Now, I know what some of you might be thinking. Half-wave rectifier, really? Aren't those things incredibly inefficient? And look, you'd be absolutely right. For any real high-powered job, you'd almost never use one. They push a DC current component back into the AC source, which is a huge no-no. It can actually saturate the core of a transformer. So, that begs the question, right? Why on earth are we dedicating a whole detailed explainer to it?
Well, this is why. This is the whole promise of our session today. The half-wave rectifier isn't just a circuit. It's an analytical gymnasium. It's where you build the mental muscles to tackle much more complex systems down the road. The math, the switching behavior, the messy real-world effects, all the fundamental building blocks are right here. If you can master this, you're truly ready for anything. All right, so here's the game plan. We're going to start with the ideal case, which seems deceptively simple. Then we'll throw in the one component that changes everything, the inductor. After that, we'll look at some practical, real-world loads and filters. Then we'll see how engineers actually improve and control these circuits. And finally, we'll touch on some of the advanced tools that the pros use.
Okay, let's kick things off with part one, the simple rectifier. We've got to start with our ideal foundation before we can start adding in all the real-world messiness. And the simplest possible case, that's a rectifier with a purely resistive load.
So in a perfect world, right, we imagine our diode is a perfect switch. As soon as the AC voltage coming in is positive, boom, the switch closes and current flows. The second that voltage turns negative, boom, the switch instantly opens and everything stops. The result is exactly what you see here. We've literally just chopped off the entire negative half of the input sine wave, leaving just these positive bumps.
Okay, and this slide, this is where people trip up all the time. For this new, bumpy waveform, we have two totally different but really important ways to measure it. The average value, that's the peak voltage, Vm, divided by pi, tells you the DC component. It's what a normal DC voltmeter would actually show you. But if you want to figure out how much power is being turned into heat in that resistor, you need the RMS, or root mean square value. For this waveform, that's Vm divided by 2. The big takeaway here is never, ever confuse average and RMS. One is the DC level, the other tells you about heating power.
All right, on to part two. We're about to add some complexity. We've handled the simple resistor, but let's be real. Most loads in the world, like motors, have inductance, and you're going to see how just one little component throws a huge wrench in the works and changes everything. So here's the deal with inductors. They store energy in a magnetic field, and the number one personality trait is that they hate change. They resist any change in the current flowing through them. So, as our AC voltage crosses zero and goes negative, a simple resistor would just let the current stop. But the inductor, full of stored energy, basically says, whoa, not so fast. It pushes back, forcing current to keep flowing, which keeps that diode turned on well into the negative part of the input cycle. And that leads us to a brand new, super important concept for our waveform. The current doesn't just stop at 180 degrees anymore. It keeps going until that inductor has finally burned through all of its stored magnetic energy. That exact moment, the angle where the current finally trickles down to zero and the diode can finally shut off, we call that the extinction angle, and we use the Greek letter beta to represent it.
And this is exactly why we called this an analytical gym. To find that one little point, beta, there's no simple algebra you can do. The equation describing that current involves sines and exponentials all mixed together. It's what mathematicians call a transcendental equation. The only way to solve it is to get a computer to make a series of educated guesses over and over until it gets closer and closer to the right answer. Suddenly, our simple little circuit needs some pretty heavy-duty math to solve.
Okay, let's move into part three. It's time to bring this out of pure theory and see how it actually works in the real world. We're going to look at two super common applications, charging up a battery and building a smooth DC power supply. So first, we'll break down what happens when our load isn't just a resistor and inductor, but also includes a DC voltage source, like a battery. Then, we'll see the classic trick for smoothing out that bumpy DC output by using a capacitor filter. So think about it like this. You're trying to charge a battery. That diode is like a one-way door, but it's got some back pressure from the battery itself.
The diode won't open up until the voltage trying to get in is higher than the voltage already in the battery. This means the diode doesn't turn on at 0 degrees. It has to wait until the AC input climbs high enough. That point where it finally turns on is what we call the delay angle alpha.
Okay, so what about our other big application, making a DC power supply? That pulsating DC is pretty useless for most electronics. The fix is to put a capacitor across the load. It acts like a little super-fast recharging battery. When that AC pulse comes through, the capacitor charges all the way up to the peak. Then, as the input falls off and the diode shuts down, the capacitor slowly drains its energy into the load. This makes the output way smoother, but it's not perfect. You get this small variation, and we call that the ripple voltage. And obviously, the smaller that little ripple is, the cleaner and better our DC power is.
All right, part 4. Now we get to the fun part, the engineering solutions. We've seen how these circuits work, and we've seen some of their problems, like that voltage going negative when you have an inductor. So now, let's talk about the clever solutions engineers use to make them perform better and to get them under control. This right here is one of my favorite, most elegant tricks in all of power electronics. On the left, you've got the standard circuit where the inductor's energy forces the voltage negative. That's just wasted energy. On the right, we add one simple component, a second diode called a freewheeling diode across the load. Now, when the main diode turns off, that inductor current has a new path to flow, to freewheel locally. This instantly clamps the output voltage at 0. It's so much more efficient and gives you a much cleaner waveform. And you know, because that freewheeling diode gives us such a nice, clean, perfect halfway output, it opens the door for us to use a really powerful tool from mathematics. We can now apply the Fourier series. This is basically a mathematical superpower that lets us take any repeating waveform, no matter how weird it looks, and break it down into a simple sum of pure sine waves at different frequencies. We call those frequencies harmonics.
So what's the big reveal from all this fancy math? It tells us that our output waveform is made of two things, the DC component that we want and a bunch of unwanted AC sine waves. And get this, for this exact waveform shape, the biggest troublemaker, the loudest piece of noise is always at double the input frequency. So if your input is 60 Hz, your biggest problem is at 120 Hz. And knowing that is huge because it means we can design filters to specifically target and eliminate that one frequency.
But what if you don't just want one fixed voltage? What if you want to control it, maybe with a dial, like on a variable power supply? For that, we need to upgrade from a simple diode to something we can control. We swap it out for a device called a thyristor or an SCR. Think of it like a diode with a doorbell. It won't turn on, even if the voltage is right, until you give its gate a little trigger pulse. By controlling when we send that pulse, we can intentionally delay the turn on by that same angle, alpha. And by changing alpha, we can precisely control the average DC voltage we get at the output.
Okay, part 5. We're on the home stretch now. This is where we stop pretending things are perfect and look at how the real world messes things up. We're talking about advanced analysis and the tools we use to deal with it.
So, up to this point, we've been living in a fantasy land where our AC source is perfect. But in the real world, every single wire, every transformer winding has a tiny bit of inductance. We call it source inductance. And just like our load inductor, it hates change. This means that when it's time for our diode to switch off, the current can't just slam on the brakes and stop instantly. It takes a tiny, but very real amount of time to ramp down. The time it takes for this current handover to happen is called the commutation angle, and we represent it with the letter U.
And this little delay, this commutation process, it isn't free. There's a cost. During that brief overlap time, it actually steals a little chunk of voltage right out of our output. You can see it as a little notch in the waveform. And what that means is that it lowers our average DC output voltage. This is a real-world voltage drop that engineers have to plan for, and it gets worse if the source inductance is higher or if you're drawing more current.
So you might be wondering, with all this crazy math and these weird real-world effects, how does anyone actually get anything done? Well, they use professional-grade tools. First up is simulation software, like PSpice. Instead of killing yourself trying to solve those transcendental equations by hand, you just build the circuit virtually and let the computer do the heavy lifting. The other big one is a pretty advanced mathematical technique called state-space averaging. It's a way to create a single, unified mathematical model that describes both the on and off states of the circuit. And that is absolutely critical if you want to design the kind of stable, smart feedback controllers that all modern power electronics depend on.
Wow, we have covered a ton of ground here, all the way from a perfect switch to the messy realities of commutation. And now I really want to hear from you. As you were following along, what was the toughest part to wrap your head around? Was it the concept of the commutation angle and how it steals voltage? Or would you find it more useful to actually see a full step-by-step walkthrough of how to build and simulate one of these circuits in PSpice?
Seriously, drop a comment down below and let me know. Your feedback really does help me figure out what to cover next. If this masterclass helped you connect some of the dots, I'd really appreciate it if you'd subscribe for more deep dives just like this one and give this explainer a like. It honestly makes a huge difference. Thanks so much for sticking with me through this deep dive. I'll catch you in the next one.